Good evening, everybody. So, in the previous lecture, we discussed on the pipe networks. So, in the pipe networks, which is really the practical application of pipe flow analysis, we discussed on what are the necessary conditions to be satisfied in the case of a pipe network. Once the necessary conditions are satisfied, then what is the method? It is basically Hardy-Cross method, the Hardy-Cross method, which is a method of successive approximations, is used for pipe network problems. So in that connection, we have mentioned that we start assuming a discharge value, and then based on that discharge, in each loop, we calculate the head loss for each pipe in that loop, and finally net head loss also we will calculate in each loop. That means the head loss in the clockwise direction is taken as positive, whereas the head loss in the anti-clockwise direction is negative. So if the net head loss in each loop is equal to 0, then the assumed values of Q in each of the pipe in that loop are correct. If not, a correction has to be applied for each pipe in that loop. After applying correction for the discharge, then again with this new discharge, we need to find out the head loss. Again, net head loss in each loop. If the net head loss again is equal to 0, then this discharge is correct. Still, if this is not 0 net head loss, then again correction has to be applied. And with this new correction, that discharge has to be modified in each pipe. After modifying that discharge, again do that. This process is repeated in each loop for each pipe of the loop till the net head loss in each loop is equal to 0. So that was the thing morning we mentioned. And in that process, we mentioned about the equations that which we will use. For head loss is the only thing, because discharge we assumed. So naturally what we need to find the velocity in each pipe. So once the velocity is obtained, the head loss in each pipe. This is what our basic thing. So for head loss, the equation you all know that it is Darcy-Weisbach equation, which is HF is equal to FLV squared by 2GT. Using that equation, if I write V is equal to Q by A, so that means Q by pi by 4 D square whole square, right? Right. If you now take it, FL V square means Q square by A square, Q square by pi by 4 D square whole square. So FL by 2GD into Q square divided by pi by 4 D square whole square. So that all depends again. Q square, if you separate it out, the rest of the things, if you take it, right, that means in the numerator FL will be there. In the denominator, it is 2G into pi by 4 whole square into d to the power of 5. All this factor is what we call it as R. So therefore, HF is equal to given by R into Q square. This is what we have given in the morning. While telling that, I stopped the lecture at the point, what is the correction that is to be applied, how it is to be applied. So that part we will continue and go into The last topic of this is branched pipes. So that's what I wish to take it. So it is a continuation to pipe networks, and where I stopped is correction for discharge. This correction for discharge is given by delta Q, which is equal to sigma of R Q naught square R Q naught square divided by sigma of 2R Q naught with minus sign, where Q naught is the initial discharge assumed in the pipe. R is equal to FL by basically 2G into pi by 4 whole square into d to the power of 5 for any pipe. So knowing R, knowing Q, you can calculate. Then after calculating this delta Q, then actually what should we do is this delta Q, how to do it? If delta Q is positive, if delta Q is positive, it should be added, it should be added to the flow in the pipe. That is, the new discharge Q is equal to Q naught plus delta Q. So this is how. If delta Q is negative, it should be subtracted from the flow in the pipe. So in such a case, Q is equal to Q naught minus delta Q. So these are the two equations which we do it. Then actually, if there are common pipes for the loops. For example, if I take it, this is the pipe. Suppose if I take it, so this is in, this is out. For example, if I take it A, B, C, D, right? This is the thing. D, after D, basically E, F, G. For example, if that I take it like this, then in such a case, this is first loop is ADBC. ADBC loop, if you take it, similarly, if you take another loop, DFE, another loop, if you take FCG, another loop, and if you take it EFG, there are four loops here. Now, if you see this, basically, for example, DF and FC, DF and FC are common for number one loop, basically two, three, four loops. So this DF is common for 1 and 2. Then FC is common for 1 and 3. Am I right? Then FE is common for 2 and 4. Then FG is common for 3 and 4. If there are common pipes for the loops, Then what should we do? Then the correction should be applied. Correction should be applied twice. Correction should be applied twice in such a case actually. So that means two corrections. So this is the only change from the morning. So please add this. Then after these corrections, take this new discharge and repeat the process. Repeat the process till the net head loss in each loop is equal to 0. Then the discharge in the pipes is correct. So it started with a trial value, and for the trial value corrections we applied, then go on again doing the second time, again basically applying correction till actually the net head loss is 0. Now last topic is the flow through branched pipes. This is also basically a short note. Flow through branched pipes. What is branch pipe basically? Branch pipe means actually when three or more reservoirs, when three or more reservoirs are connected by pipes, that is called as branch pipe, branched pipes. What is that meaning actually? For example, you take, I have one reservoir here. I have one more reservoir here. I have one more reservoir here. There are three reservoirs. The three reservoirs are such that if I take a common thing, right? Suppose if you take the water level in this is up to here. In this, the water level is up to here. This water level is here. Suppose now if I take the datum starting point, this is the datum. For example, if I treat this as reservoir A, this is ZA. Similarly, if I treat this actually as B, for example, then this is ZB. And if I treat this as ZC, then this is ZC. Starting point, right? If this is this. Now, basically, if these are connected by pipelines, for example, like this. These are all the three pipes. So this is first pipe, for example, this is second pipe, this is third pipe, three pipes, right? And if I make it actually, what will happen? This I make it the junction as D, right? Now, if that junction is at what datum actually, at D, I can take it, right? If this is the, this velocity in this pipe, if I take it, it is V1, right? Its length is L1 its diameter is D1, and it's basically the head loss through it is HF1. Similarly, here if I take it V2, L2 is the length, D2 is the diameter, HF2 is the head loss. Head loss is equal to FLV squared by 2GD. Here this is V3, L3, D3. This is equal to HF3. So this is what basically the things. So now my job is how to analyze the problems. So what are the unknowns in this? The unknowns are V1, V2, V3 I should find, and what is the pressure here? Because this is a free surface, so naturally here, for example, if I take it, it is 0. Here it is also free surface, it is also 0 because it is atmospheric pressure. And here if I take it again, PC is equal to 0. So these three I know. But what is not known to me, what is PD is not. So this is one question. So the unknowns are what is the velocity here, velocity here, and what is PD. These are the four unknowns. The four unknowns in this problem are the four unknowns in the above problem are above problem means I mean branched pipes are right V1, V2, V3 and PT. These are the four. So we need four equations to solve the above four variables. What are the four equations? The four equations are number one is continuity equation, number two it is Bernoulli's equation, and three basically Darcy Weisbach equation. So using these three equations, we should be able to generate some equations to determine the four variables. How I will do? Then what I will start with basically. So number one, first is I applying Bernoulli's equation between A and D. For example, if I apply like that, pressure at A is equal to 0 because atmospheric pressure. Then the velocity in the tank at the free surface is 0. So V squared by 2G is 0 plus ZA is equal to then PD by gamma W plus again basically there the velocity, that means when the flow enters at the junction, velocity becomes 0. So velocity is 0 there. Again datum is ZD plus head loss from A to D in the first pipe, head loss in the first pipe. This is one equation, right? Applying Bernoulli's equation between D and B, if I apply D already I have drawn here, PD by gamma W plus 0 plus ZD plus basically is equal to at D I have applied. Then I go to B. B I go. Then B again atmospheric pressure in the tank B. Again basically the velocity head 0 in the tank plus basically what next one is ZB plus HF2. This is second equation. Then applying Bernoulli's equation between B and C, it is PD by W gamma W plus velocity 0 at the junction plus ZD is equal to in the tank C pressure is atmospheric pressure. At the free surface the velocity is 0 plus ZC plus HF3. So this is 3. And then basically then applying continuity equation, basically we can write it actually if I say it discharge in AD is equal to discharge in DB plus discharge in DC. So therefore finally it is Q1 is equal to Q2 plus Q3. Pi by 4 T1 square into V1 is equal to pi by 4 T2 square into V2 plus pi by 4 T3 square into V3. So this is fourth equation. So now there are four equations to solve four unknowns V1, V2, V3. Then last one is PD by gamma. So then if you solve it, solve the variable. So what is branch pipe? Actually, if two or three pipes are connected, if suppose if I take one is this, now one is this, and one more is going like this. If these like three pipes, one, two, three, are connected to reservoirs, then we call it as, for example, right? If we connect like this, how to solve this problem and find the pressure at this junction. So this is what the branched pipe system means. So with this, the first part of pipe flow is over. So what are the things I have covered? Go to lecture 1, Reynolds experiment. Then what I have done next, actually, lecture 2, this is losses in pipe flow. What is lecture 3? The major loss, that is Darcy-Weisbach equation. What is lecture 4? hydraulic gradient line, energy gradient line. What is lecture 5? We have taken up pipes in series. What is lecture 6? Pipes in parallel. What is lecture 7? I have taken it up what you call it as pipe networks. What is lecture 8? I have taken it up branched pipes. So this is what your total entire what you call it as pipe flow is. In this topic, where the problems, this is one area where problems, this is second area where problems, this is third area where you get problems, this is fourth area. So these four types of problems you should do it in this, whereas remaining are all theory questions. We close down this topic at this stage and then take up the next part of the unit. With this, the one part is completed. So with this lecture 8, we have completed the pipe flow analysis. In this pipe flow analysis, again I am repeating that the problems on lecture 2, problems on lecture 3, and problems on lecture basically 5 and 6. Four problems are there. Kindly work on the problems. We have solved the problems also in the lecture itself. So that completes the pipe flow. So the pipe flow is only 50% of unit 4. So unit 4, 50% we have completed. So the second 50% of unit 4 is the boundary layer, and that we have to take it up. So in the next lecture, I will take up the boundary layer theory. Right? Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.